Welcome to Simplified UPSC by PPP, where we listen, learn, and grow together. Detailed lecture notes in English and Hindi, plus practice questions for prelims and mains, only on our Telegram channel. Link in description. Like and subscribe for more.
Welcome to the deep dive. If you're looking for a solid, comprehensive, but still quick way to get your head around environmental pollution, the real foundational stuff, the science, the sources, the solutions, well, you're in the right place. Today, our mission really is to build that strong base. We want to get past the headlines and really master the specific terms, the causes, the impacts of pollution across air, water, land, the whole picture.
Exactly. And we'll be systematic about it. We're going to walk through each type: air, water, land pollution. We'll break down the specific pollutants, look at where they come from, their effects, and crucially, dig into the control technologies meant to deal with them. The aim here is that by the end, you'll have real factual clarity, but also that deeper conceptual grasp of, well, the burden we're placing on the environment through, all this activity.
Okay, right. Let's start unpacking that. So fundamentally, the sources define pollution pretty simply, don't they? It's basically adding stuff or too much stuff to the environment, air, water, soil, to the point where it becomes less suitable or even, totally unsuitable for life.
That's the core idea, just making it unfit.
And when we look at what's driving this, especially air pollution in, say, the modern era, it seems like there's a really direct link, almost unavoidable, isn't there, between more traffic, growing cities, rapid economic development, industrialization.
Absolutely. Those are the engines generating the pollutants.
Yeah.
And the technical definition, if we want to be precise, air pollution is defined as contaminating the air with one or more contaminants. And the key part is in such quality and duration as to be injurious. That word injurious is powerful. It means causing harm to human health, welfare, animals, plants, even property. So it's not just about hazy skies. It's about actual measurable damage from these substances in the air.
Right. Injurious. That hits hard.
Right.
Okay, so let's get into the specifics of what's in that air. It's not just one thing, is it? It's a complex mix.
Oh, definitely not simple. It's a chemical soup, as you say. We should probably start with the main gaseous pollutants, the ones really driving respiratory problems.
Sounds good. Where do we begin?
Let's start with the oxides. They're central to a lot of issues, both health and atmospheric. First up, sulfur oxides, or SOx. These are nasty, corrosive gases. And the primary source, big combustion processes, think thermal power plants, heavy industries, basically burning fossil fuels that contain sulfur.
Okay, power plants, industry, and the health effects. You mentioned corrosive.
Yeah, they irritate the eyes, the throat, they cause coughing, allergies. But more deeply, they actually mess with enzyme function in your respiratory system, which, well, makes it harder for your lungs to do their job, exchanging gases, getting oxygen in. It's like a direct attack on your breathing mechanism.
Wow, okay. And often when you talk about SOx, NOx isn't far behind, right? Nitrogen oxide.
Exactly. They often come together. Nitrogen oxides, LOX sources, or even broader, actually, comes from burning pretty much any fuel, petrol, diesel, especially coal. So, again, thermal power plants, industry, but also vehicles are a huge source. And NOx isn't just bad on its own. It's a key ingredient in making ground-level smog. And, as we'll probably get to later, it's a precursor to acid rain.
Okay, so multiple impacts. And the direct health toll.
Significant irritation, inflammation of the lungs, leading to breathlessness, long-term exposure. It's strongly linked to things like bronchitis, asthma, making them worse or even causing them. And the source specifically points out that kids are more vulnerable. High NOx levels make them more susceptible to respiratory diseases, especially in winter.
So stepping back for a second, what we're seeing is this direct line. We need energy, we need transport. That's modern life, modern economy. But the consequences, well, a rising tide of serious chronic breathing problems in people. It's a trade-off right there in the data.
It's an inescapable link, absolutely. Now, shifting from gases to solids, or tiny particles, really, we need to talk about suspended particulate matter, SPM. This isn't just one chemical. It's a mix, fine solid bits, liquid droplets, smoke, dust, vapor, just hanging in the air.
And where does SPM come from? Same culprits.
Largely, yes. Vehicular emissions are a big one, and burning fossil fuels on a large scale. The real problem with SPM is the size. The smaller the particle, the deeper it gets into your lungs. It causes serious lung irritation. It can even reduce the development of red blood cells, which is a systemic issue, and leads to pulmonary malfunctioning, basically your lungs not working right. And, conceptually, SPM is what makes haze. That visible reduction in air clarity in cities, that's largely SPM.
Right, the visible stuff. And then there's the invisible killer, carbon monoxide, CO. Odorless, colorless, toxic.
CO, yeah. It's formed when things don't burn completely. So vehicle exhaust again, burning fossil fuels, but also smoke from biofuels. Think indoor cooking fires in some places. The danger with CO is how it works. It binds to the hemoglobin in your blood way better than oxygen does, so it basically stops oxygen getting around your body. Suffocates you from the inside out.
That's terrifying. And the symptoms are immediate.
Yes. Acute. Difficulty breathing, really bad headaches, irritation of mucous membranes. If the concentration gets high enough, it leads to unconsciousness and, well, death. Quickly.
Okay, it's vital to distinguish that immediate threat from its chemical cousin, carbon dioxide, CO2. CO2 is mainly known as the big greenhouse gas, but the source lists it as a pollutant too, with direct health effects.
That's correct. While its main impact is climate change, high CO2 levels, especially indoors or in confined spaces, aren't harmless. The source notes it can impair reflexes, judgment, even vision, and cause severe headaches, put a strain on the heart. So even CO2, when concentrated, poses a direct, immediate risk to how well we function.
Interesting. Okay, one more major one in this category, ozone, but specifically the bad ozone, right? The ground level stuff.
Right, tropospheric ozone. This is different from the good ozone layer high up. This bad ozone is a secondary pollutant. It's not emitted directly. It forms from chemical reactions between other pollutants, specifically NOx and things called volatile organic compounds, VOCs. And these reactions need sunlight. That's why it's linked to photochemical smog. Think sunny urban areas with lots of car emissions. That's the recipe.
Secondary pollutant formed by reactions. Got it. And the consequences.
Pretty severe. Breathlessness, triggering bad asthma attacks, wheezing, chest pain. If you're exposed long-term, it's linked to really serious, irreversible lung conditions like emphysema and chronic bronchitis. Plus, it irritates your eyes, makes them itch, burn, water. And maybe most insidiously, it actually lowers your body's resistance to everyday illnesses like colds or even pneumonia. So the key takeaway is that the pollution cocktail is often more dangerous after it's been cooked in the atmosphere by sunlight.
Okay, so beyond those major gases and particulates, the sources highlight some specific industrial nasties, toxins that seem almost historical but are still active threats.
They are indeed. Heavy metals are a big concern. Let's start with lead, BB. Historically, the main source was leaded petrol. Thankfully, that's mostly phased out in many places, but not everywhere, and the legacy remains in the soil. Lead is a neurotoxin, and it hits children hardest. It causes permanent brain and central nervous system damage, kidney problems, and fundamentally messes with red blood cell development, which leads to impaired intelligence, learning difficulties. It's truly tragic, an industrial byproduct causing irreversible harm to kids.
Just awful. What other metals or dusts are highlighted?
Well, there's cadmium, often from industrial processes, and the source specifically flags it as affecting the heart. Then you have these dusts linked to specific jobs. Silica dust, you find this in silicon quarries, mining. It leads to a severe lung disease called silicosis, often fatal. Cotton dust, from cotton textile factories. This causes bisonosis. It's nasty, destroys lung tissue, causes chronic cough, bronchitis, eventually emphysema. And then there's asbestos dust, probably the most well-known. Comes from asbestos mining, making asbestos sheets. It causes asbestosis, which means severe respiratory problems and a very high risk of cancer later on.
It's actually quite shocking, isn't it, that these specific named industrial diseases, silicosis, bisonosis, asbestosis, are still listed as major hazards, you'd think, with regulations and awareness. But clearly there's a gap between the rules and what's happening on the ground.
It definitely points to ongoing challenges with enforcement and, well, maybe legacy industries. But let's shift gears slightly. From the factory to the home and office, because the source makes a really interesting point about indoor air pollution. How our efforts to make buildings energy efficient, sealing them up tight, have ironically trapped pollutants inside.
Right. So what are the main things causing poor air quality inside buildings?
Well, the reduced ventilation is key. Air doesn't circulate, so contaminants build up. And the contaminants come from the building materials themselves. Synthetic stuff, carpets, particle boards, insulation foam. Plus all the chemical products we use, cleaners, pesticides, air fresheners. Two specific indoor hazards are highlighted. First, formaldehyde. This gas leaks out of things like carpets, particle board furniture, foam insulation. It causes eye and nose irritation, triggers allergies.
Okay, annoying but maybe not deadly. What's the other one?
The other one is more serious, radon. Radon is actually a naturally occurring radioactive gas. It seeps up from the soil and rock beneath buildings. Normally, it would disperse. But in modern, tightly sealed, poorly ventilated houses, it gets trapped and concentrates. And it's highly carcinogenic. It's a known, significant cause of lung cancer. So it's a natural hazard made worse by our building practices.
Radon. radioactive gas in our homes. That's unsettling. Before we leave air pollution, let's circle back to something you mentioned earlier, a specific byproduct of power generation, fly ash. It sounds like a major disposal issue.
It is, in terms of volume. Fly ash is that fine, powdery residue left after burning coal in thermal power plants. Its direct hazard is localized. It can settle on plant leaves near the power station, physically blocking sunlight and pores, which reduces crop yield.
But it's not all bad news. The source mentions advantages, ways to reuse it, almost like turning waste into a resource.
It's exactly. There's a big policy push to utilize fly ash because there's just so much of it. And the advantages are pretty compelling. One, it can replace a good chunk of cement and concrete up to 35%, the source says. That cuts construction costs and saves resources. Two, it's great as a filler material for building things like road embankments or making lightweight bricks. Three, and this is important for environmental repair, it can be used to reclaim wastelands. Specifically, filling in old abandoned mines or quarries, turning scarred land back into something potentially useful.
So the challenge is scaling up that reuse to match the sheer amount being produced.
Precisely. Finding enough economic uses for the vast quantities. And just to close the loop on air, remember those precursors we mentioned? The ones causing problems far away. Acid rain. This really shows how pollution doesn't respect borders.
Right. What were the key gases again?
The source clearly states it's caused by nitrous oxide, Eros-X, and sulfur dioxide, and yellow-X. These gases travel long distances, react chemically in the atmosphere with water and oxygen, and then fall back to Earth as acidic rain, or even snow or fog. Highly damaging.
Okay, we've painted a pretty detailed and frankly concerning picture of air pollution. So what about fixing it? What control measures are mentioned?
Right, solutions. The approach needs to be multi-layered. Engineering, changing processes, policy. The general strategies fall into a few categories. You can try to destroy the pollutants, maybe burn them at high temperatures or use a catalyst. Or you can convert them into something less harmful. Or you can physically collect them before they get out.
And for industries specifically?
Well, ideally, you modify the industrial process itself so it produces less pollution in the first place. Site selection and zoning are also crucial. Building plants away from residential areas. Using really tall chimneys to help disperse what's left, though that just spreads it out, doesn't really solve it.
Right. And for the particulates, the smoke and dust, the SPM, are there specific technologies?
Yes. Two key devices are mentioned for controlling particulate matter: arresters and scrubbers. Arresters, like electrostatic precipitators, use electricity to pull solid particles out of the exhaust gas. Scrubbers, meanwhile, usually spray a liquid, often water, into the polluted airstream. This traps particles and can also absorb some harmful gases.
It strikes me that all these controls, changing processes, installing scrubbers, zoning, they all cost money, significant money for industry. And that really highlights the core policy challenge, doesn't it? Trying to enforce these potentially expensive safeguards while also pushing for economic growth. That tension must be where regulations sometimes fall short.
That's exactly the pinch point. Balancing development with environmental protection, it's a constant struggle in implementation.
Okay, let's shift our focus now. From the air we breathe to the water we depend on. Water quality is just fundamental, isn't it? But how do we actually measure how polluted water is? Is there a standard test?
There is. The key concept, the standard benchmark for checking pollution in water bodies, is biological oxygen demand, or BOD. It's defined as the standard criterion for pollution assay in aquatic ecosystems.
Biological oxygen demand. Okay, what does that actually mean? What's it measuring?
Conceptually, BOD measures how much dissolved oxygen is needed by the aerobic microorganisms, the little bugs that need oxygen to break down the organic waste present in a sample of water. It's usually measured over a set time, like 5 days, at a specific temperature.
Okay, so wait, if the BOD is high, does that mean there's a lot of waste and the microbes are working overtime, using up lots of oxygen to decompose it?
Exactly. You've got it. A high BOD means high levels of organic pollution. The water is biologically demanding a lot of oxygen to clean itself up. It signifies a heavy pollution load.
And the consequence of that high demand, that high BOD, that leads to problems like eutrophication, right?
Precisely. High BOD is intimately linked with eutrophication. That's the whole process of an ecosystem degrading because it's overloaded with nutrients. What happens is you get too many nutrients, usually nitrates and phosphates, often from sewage or fertilizer runoff, pouring into a lake or river. These nutrients act like super fertilizer for algae and phytoplankton. They just explode in growth, creating those thick algal blooms you sometimes see.
The green scum on the surface. And that bloom looks bad, But the real damage happens when all that algae dies.
That's the critical point. When that massive amount of algae dies, that decomposes those aerobic microbes, again go into overdrive, breaking it all down. And that process consumes huge amounts of the dissolved oxygen, DO, in the water. Oxygen levels plummet. Fish and other aquatic animals start to suffocate and die off. Then the system can flip to become anaerobic without oxygen. This favors different kinds of bacteria, some of which produce toxins. The whole ecosystem just collapses.
And temperature plays a role too.
Yes, a crucial one. Oxygen dissolves less easily in warm water. Plus, warmer water speeds up the metabolism of those decomposers, so they use up oxygen even faster. So, heat makes the whole DO depletion problem significantly worse. Climate change linkage right there.
Okay, so eutrophication is a clear sign of man-made pollution. What are the main sources driving it?
The sources are pretty clear. Untreated sewage being discharged from towns and cities, that's a huge one. Runoff of chemical fertilizers from agricultural fields. Rain washes it into streams and rivers, and large amounts of animal waste from concentrated livestock farming.
Right. And thinking bigger, globally, what about pollution in the oceans? Marine pollution.
Marine pollution is a massive issue. The sources mentioned include obvious disasters like oil spills, the ever-growing problem of plastic waste, which physically harms marine life and breaks down into microplastics, and also the constant discharge from rivers carrying all sorts of pollutants, industrial waste, agricultural chemicals, sewage out into coastal waters and the open ocean.
Let's zoom back into a specific, critical problem in India: groundwater pollution. The source flags particular contaminants causing health crises.
Yes, it highlights two major culprits contaminating drinking water in various parts of India: arsenic and fluoride. Arsenic contamination is often linked to the geology itself, especially in river basins like the Ganga. Under certain conditions, arsenic naturally present in the soil gets mobilized into the groundwater. Fluoride also often comes from natural geological sources, leaching out of certain types of rock. Both cause severe chronic health problems, skeletal issues from fluoride, various cancers, and skin problems from arsenic. It's a major public health challenge.
And there's a link mentioned between human activity like sand mining and groundwater health. That seems less obvious.
It does, but it's important. The source points out that heavy sand mining in riverbeds can have serious consequences. Sand in a riverbed isn't just sand. It acts like a natural filter and helps recharge the aquifer. Removing too much disrupts the river's ecosystem, and the source suggests this can lead to pollution of the groundwater underneath. Plus, removing that sand barrier can actually lower the water table locally. And near coasts, it increases the risk of salty seawater intruding into freshwater wells. It's quite destructive.
Given the scale of river pollution, especially the Ganga, what policy responses are mentioned? There was the Ganga Action Plan, GAP.
Yes, GAP was launched way back in 1986, a pioneering effort for its time. Its main goal was pollution abatement, basically cleaning up the river. The strategy focused on intercepting, diverting, and treating sewage and industrial waste from the biggest polluters along the banks, a major infrastructure project.
And more recently, there's the Clean Ganga Fund, CGF. That sounds like a different approach.
It is, in a way. CGF focuses more on harnessing public support and, well, money. It allows for voluntary contributions, not just from people in India, but also NRIs and PIOs abroad. And the money funds a wider range of activities, tackling non-point pollution that diffuse stuff like agricultural runoff, open defecation near the river, cattle wallowing, which is harder to control than factory pipes, setting up new waste treatment plants, of course, and importantly, investing in conserving the river's biodiversity, the unique plants and animals that depend on it. #3, land, soil, and waste pollution.
All right, let's move on to the land itself, the soil beneath our feet. It's the foundation for so much, but it's also under attack.
Absolutely. Soil faces immense pressure. Things like widespread deforestation and large-scale mining directly cause soil erosion. The fertile topsoil just washes or blows away. And what remains can be degraded further. Industrial waste dumps toxic substances into the soil. And modern agriculture often relies heavily on chemicals, pesticides, herbicides, things like DDT, which persist for a very long time.
Speaking of persistent waste, the sources bring up a distinctly modern problem: e-waste. All our old computers, phones, gadgets.
Yes, electronic waste. It's a huge growing issue because electronics contain a nasty mix of valuable and toxic materials. Improper disposal, just dumping it or burning it in uncontrolled ways, which happens a lot, releases these toxins. And the list of specific heavy metals found in e-waste is quite alarming. It's something worth memorizing.
Okay, let's hear it. What's on that critical list?
The source specifically lists these as being released into the environment from e-waste. 1, beryllium. 2,
Cadmium.
3, chromium. 4. Heptachlor. Actually, that's a persistent organic pesticide, not a metal, but it's listed here as a key hazardous component in some electronics. 5. Mercury. 6. Lead. And 7. Plutonium.
Plutonium, really, in everyday electronics.
Likely in very specific, maybe older or specialized applications, perhaps smoke detectors or certain instruments. But its presence on the list, alongside known toxins like mercury and lead, really drives home that e-waste isn't just junk, it's hazardous material. Managing it properly is critical.
Absolutely. Okay, let's go back to those persistent chemicals you mentioned, like DDT. Why are these non-degradable pollutants so dangerous?
Well, DDT is the classic example. It's an insecticide that was used everywhere. The problem is it doesn't break down easily in the environment. It lasts for years, decades even. So every time it's applied, the concentration in the soil and water just keeps going up.
But the real danger isn't just its presence, it's how it moves through the food chain, right? This idea of biomagnification.
Exactly. That's the killer aspect.
Yep.
DDT gets into the environment, then into small organisms, then into the fish that eat them, then into the birds that eat the fish. At each step up the food chain, the concentration increases dramatically, and it has specific damaging effects. It messes with hormones, estrogen and testosterone activity gets depressed. The most famous example is in predatory birds. DDT interferes with how they metabolize calcium for eggshells. The result? Thin, fragile eggshells that break before the chicks can hatch. It devastated populations of birds like eagles and pelicans.
A truly insidious effect. And another element that biomagnifies is mercury.
Yes, mercury is flagged as one of the most common and toxic heavy metals in water bodies, often from industrial discharge. In water, it often converts to an organic form called monomethyl mercury, which is particularly nasty and easily absorbed by organisms.
And mercury poisoning has led to infamous health disasters.
It has. Minamata disease in Japan is the classic, tragic example, though not explicitly named here. The source notes mercury causes fatal poisoning, and it points out high levels have been found in fish stocks in specific areas like Mumbai, Kolkata, Karwar, and the North Col River. And get this for toxicity. The source states mercury is about 1,000 times more potent than colchicine, which is itself a highly toxic substance. Just shows how dangerous it is, even in tiny amounts.
1,000 times. Wow. Okay, before we move to solutions, are there other types of pollution mentioned?
Yes, a couple more to cover briefly. First, noise pollution. We don't always think of it like chemical pollution, but it has real impacts. The source notes that monitoring noise levels is actually part of the Environmental Impact Assessment, EIA, process for big projects. EIAs have to assess existing noise levels and predict how much noisier things will get due to, say, construction or increased traffic.
So noise is officially recognized as an environmental impact. Interesting. What else?
Second, thermal pollution. This is basically releasing warm or hot water into rivers or lakes, usually from industrial cooling processes like at power plants. That warm water affects water quality directly. And as we discussed with BOD and eutrophication, warmer water holds less oxygen, and it speeds up decomposition, further depleting oxygen and stressing or killing aquatic life.
Okay, let's pause here and try to synthesize a really crucial concept that's come up repeatedly. We've talked about all these pollutants, DDT, mercury, lead, cadmium, and a key feature for many of the most dangerous ones is that they are non-degradable. They don't break down. Why is that property the inability of nature to metabolize them? Why is that so fundamentally dangerous for ecosystems and food chains? What's the mechanism?
That's a great question, and it gets to the heart of environmental toxicology. When a pollutant is non-degradable or breaks down very, very slowly, it sticks around. It persists. And that persistence allows two dangerous processes to happen: bioaccumulation and biomagnification.
Okay, break those down for us. Bioaccumulation first.
Bioaccumulation is what happens within a single organism. It takes in the pollutant, maybe through breathing, eating, or just contact with contaminated water or soil faster than its body can get rid of it or break it down. So over its lifetime, the concentration of that pollutant builds up inside its tissues.
Okay, builds up in one creature. Then biomagnification.
Biomagnification is what happens between trophic levels, moving up the food chain. It's a tendency for these accumulated pollutants to become much more concentrated at each higher level. Think about it. A small fish eats lots of tiny contaminated plankton. A bigger fish eats lots of those small fish. A bird eats lots of the bigger fish. At each step, the predator consumes the total accumulated dose from all the prey it eats. So the pollutant concentration magnifies dramatically, potentially reaching lethal levels at the top of the food chain, even if the initial concentration in the water was very low. That's why top predators are often most affected.
Right, that makes perfect sense, the concentration effect. And what makes a chemical likely to biomagnify? Are there specific properties we look for?
Yes, there are 4 key characteristics a pollutant generally needs to have for biomagnification to be a serious risk. It needs to be 1, long-lived, have to persist in the environment long enough to be accumulated. If it breaks down quickly, it's less of a problem. 2, mobile. It has to be able to move through the environment and get taken up by organisms. 3, soluble in fats, lipid soluble. This one is absolutely crucial. If a pollutant dissolves in water, organisms can usually excrete it relatively easily, like in urine. But if it dissolves in fat, the body tends to store it away in fatty tissues. It gets locked in, sometimes for the organism's entire life. That's why you often measure these pollutants in blubber or fat reserves, or even in milk. 4, biologically active. It has to actually do something harmful once it's inside the body. If it just sits there inertly, it might not matter as much.
Fat-soluble and long-lived. Got it. So that's the profile of the really dangerous, persistent, magnifying pollutants, like DDT, like mercury. This framework is really helpful for understanding the threat. #Biomagnification, remediation techniques, and concluding synthesis. So if we've ended up with contaminated land or water, what can we actually do about it? We need ways to clean up the mess. What remediation techniques are mentioned in the source? How do we start repairing these polluted sites?
Well, the source highlights a really interesting biological approach, Mycorrhizal Biotechnology. This fits under the general headings of bioremediation or phytoremediation, using living things like microbes or plants to clean up pollution.
Mycorrhizal, those are fungi that live with plant roots, right? How does using them help clean up degraded sites?
Exactly. Mycorrhizal are fungi that form a symbiotic, mutually beneficial relationship with plant roots. Using this biotechnology is effective for rehabilitating tough sites because the fungus gives the plant superpowers, essentially. The source lists several key benefits the fungi provide. They massively increase the root's surface area, helping the plant absorb scarce nutrients and water much better. They help the plant resist drought. Crucially, for polluted sites, they help the plant tolerate extreme soil pH, really acidic or alkaline conditions, and they can even help the plant resist diseases. So by using plants that have this mycorrhizal partnership, you can get vegetation established on really damaged or contaminated land where plants might otherwise struggle to survive. And getting plants growing is the first step to recovery.
Using nature's partnerships to heal itself. That's quite elegant. #A. Concluding. Takeaway.
Okay, so let's pull together some key factual takeaways from this whole discussion. Things to really lock in for quick recall. First, those specific Indian groundwater pollutants, arsenic and fluoride. Remember that pair. Match the disease to the dust. Silicosis from silica dust, biocenosis from cotton dust. Second, the key measure for water pollution. BOD, biological oxygen demand, is the standard criterion. Third, that list of heavy metals from e-waste needs recall. Beryllium, cadmium, chromium, heptachlor, mercury, lead, plutonium. Commit those to memory.
Right, those are the critical facts. And stepping back, what are the bigger picture insights, the connections to policy and governance? Well, transboundary pollution really stands out. Acid rain is the perfect example. Pollution from Sakasax and Nakas travels across borders, affecting places far from the source. It shows environmental problems need international cooperation. And the central recurring challenge is implementation. We know about the pollutants, we have technologies like scrubbers and bioremediation, but there's this constant tension between the push for economic development, building power plants, mining resources, industrializing, and the need to enforce environmental safeguards. That seems to be where the system often struggles.
Exactly. The knowledge and technology often exist, but bridging the gap to effective, consistent enforcement on the ground is the real hurdle.
So we've seen there are control technologies, remediation techniques like using mycorrhiza, a lot of scientific tools are available, but then you have these powerful economic drivers. Think about the demand for cheap construction sand fueling that illegal riverbed mining we discussed. When those kinds of immediate economic incentives encourage people to bypass the rules, well, how much can technology alone really achieve? It feels like if the enforcement and the political will aren't there to make the rules stick, even the best science struggles to make a difference on the ground. Making implementation work, that seems like the crucial next step.
Thanks for watching. Follow us on Telegram and Instagram. Don't forget to like, share, and subscribe.